Today, we're doing something a bit different. We're kicking off a whole new series, diving headfirst into hydraulics.
Sounds exciting. It's a huge field.
It really is. And
Yeah.
maybe not what everyone thinks of first. It's not just water under bridges. We're talking about the real unsung heroes of moving fluids, the things powering everything from, well, your own heart to massive industrial machines, often totally out of sight.
Absolutely. Hidden tech that makes the modern world work.
Exactly. So our mission for this first deep dive in the series is to really get into hydraulic machinery, but specifically we want to laser focus on pumps.
Good place to start. Foundational.
Right. We want to pull back the curtain, unpack how they work, what the main bits are, the principles behind them, some of which are actually quite surprising when you dig in. This is really tailored for, well, anyone getting into engineering. Maybe you're a student, or honestly, just if you're curious about how things work. We want to give you that solid foundation, that shortcut to understanding hydraulics right from the start.
Hmm.
And to do that, we've sifted through quite a stack of sources. Foundational textbooks on fluid mechanics, hydraulic engineering guides, practical examples, problem sets.
The whole gamut.
Pretty much. We've tried to distill the really key concepts, pull out the interesting insights, the practical stuff, so you don't have to wade through, hundreds of pages yourself.
Makes sense. Get straight to the core ideas.
Precisely. So enough talk about it. Let's actually dive into this world of hydraulic machinery.
Okay. Well, it's amazing just how ubiquitous these machines are, really woven into daily life. And fundamentally, hydraulic machinery boils down to one core purpose. These are devices built to either add energy to a fluid or, conversely, to extract energy from a fluid flow.
Add or extract energy.
Okay.
Like a push or a pull on the fluid's energy.
Exactly. It's an energy exchange. You're either pushing the fluid to do something or you're letting the fluid push something else, like a turbine.
And once you start looking, they are just everywhere. Like you mentioned, sometimes in places you wouldn't even think. Pumping up a bike tire.
Yep. Classic example. Adding energy to air, which acts as a fluid.
Or, the human heart. An incredible biological pump.
A perfect example of a positive displacement pump, actually. Tirelessly moving blood.
And then the big stuff. Industrial water pumps for cities or keeping mines dry. They're all based on these same ideas.
Absolutely. These same core principles scale up and down. Now, when we talk about fluid machines generally, they tend to fall into two main categories, big buckets, if you will.
Okay. What are they?
The first are positive displacement machines. These work on a very sort of intuitive principle. They move fluid by trapping and then physically displacing a fixed volume of it with each cycle or rotation.
So it's like capturing a specific chunk of fluid and then pushing it out, not a continuous flow thing.
Exactly. Think of a syringe or, like you said, the bicycle pump piston pushing a set amount of air, or gear pumps in engines, the gears mesh, trap oil in the gaps, and carry it around.
Even the heart, like you said.
Yeah.
Each chamber contracts, pushes out a set volume.
Precisely. It fits that model.
So what are the pros and cons of that approach? When would you choose positive displacement?
Good question. Because it highlights the trade-offs. Positive displacement pumps are great when you need really high pressures or very precise metered flow. They tend to maintain flow rate pretty well even if the downstream pressure changes a lot.
Okay, so good for pressure and precision. What's the downside?
Well, the flow is often pulsating, comes in spurts with each cycle. They can be mechanically more complex, sometimes bulkier, and generally aren't the best choice for the really, really high flow rates you see in, say, big water transport systems. Good for pressure, less so for sheer volume sometimes.
Right, makes sense. So what's the other big category?
The other major group, which operates very differently, are the turbo machines. Here, the pressure changes in the fluid don't come from trapping volumes. Instead, they result from a continuous rotary action. You have rotating blades or vanes constantly interacting with the fluid.
Okay, so not trapping and pushing, but more like that.
Essentially, yes. It's a dynamic interaction involving rotating components, impellers, propellers, runners continuously adding or removing energy.
And examples here would be like boat propellers?
Yep. Propellers, big industrial water pumps, windmills.
Windmills extract energy, right?
Exactly. And compressors, like for filling scuba tanks. They all use that rotary action.
That's a really key difference. Within those turbo machines, though, you mentioned adding or extracting energy. Is there a split there, too?
There is, and it's crucial. On one side, you've got pumps, blowers, and compressors. Their job is to add energy to the fluid. They take mechanical energy, usually from a spinning shaft, and convert it into fluid energy, increasing pressure or velocity or elevation.
Okay, adding energy. And the other side.
That's turbines. They do the opposite. They extract energy from a moving fluid, think hydroelectric dams.
Mhm.
The water flows through the turbine, spins it, and that mechanical energy is used, often to generate electricity.
Got it. Pumps put energy in, turbines take energy out.
You got it.
And for this deep dive, since it's our first one on hydraulics, we're really going to focus in on pumps. They seem like the fundamental building block for so many systems.
Definitely a good place to build from. Understanding pumps is key.
Okay, so let's start breaking them down. How are pumps classified? Like, what are the main types we should know about?
Structurally, we often classify them based on the primary direction the fluid flows relative to the pump's rotating shaft.
Okay.
So first, you have axial flow pumps. In these, the fluid generally flows parallel to the pump shaft. Imagine a propeller inside a pipe, pushing the water straight through.
Like a fan in a tube, almost.
Pretty much, yeah. Minimal sideways or radial movement.
And what makes these axial pumps special? When would you use one?
They're really good at handling very large flow rates, but at relatively low pressures, or low head, as we call it.
Head meaning height or pressure.
Yeah, basically the energy level. Think big drainage systems, irrigation, circulating water in power plants, moving huge volumes quickly, but not necessarily lifting it super high or creating massive pressure. They're often quite efficient for that specific job.
High volume, low pressure. Got it. What's the other main type?
That would be the radial flow pumps. And these are honestly probably the most common type you'll run into. They're much better known as centrifugal pumps.
Ah, centrifugal. I've heard that term a lot. How do they work differently?
With centrifugal pumps, the fluid enters near the center, near the shaft, typically along the axis. But then the rotating part, the impeller, slings it outwards, radially, perpendicular to the shaft.
So it comes in the middle and gets thrown out to the sides.
Exactly, like a spinning bucket flinging water out. That outward motion is where the energy gets added.
Okay, so that spinning, flinging action.
Yes.
That's what makes them centrifugal. Why are these so common? What's their sweet spot?
Their versatility is huge. Centrifugal pumps are great for a wide range of heads, medium to high in flow rates. And unlike positive displacement pumps, they provide a smooth, continuous flow, no real pulsation.
Makes sense. Where do we typically see them?
Oh, everywhere. Your house plumbing likely has one. Industrial chemical plants, city water supplies, fire hydrants, car cooling systems. They're really the workhorses. Plus, they're generally reliable, relatively simple mechanically, and can handle different kinds of fluids pretty well. And our sources mention a few specific configurations you might see, like a single suction, single stage pump where water comes in one side, or a double suction type which pulls water in from both sides of the impeller.
Double suction.
Yeah.
Does that just mean more flow?
Primarily, yes. It allows for higher flow rates for a given impeller size, and it also helps to balance out the axial forces on the shaft, which can be good for longevity. But the core principle, using that centrifugal force, is the same.
Okay, this is great. Let's go deeper then. Inside that centrifugal pump, what's the real mechanism? What's the part doing the work?
Right. The absolute heart of a centrifugal pump is the impeller, no question.
The impeller.
Yep, that's the rotating component. It's got a series of curved blades or vanes. And as this thing spins, sometimes very fast, it does all the work.
How exactly? What are the blades doing?
So as the impeller spins, it creates a low-pressure area at its center, the eye, which draws fluid in. Then the vanes basically catch the fluid and accelerate it rapidly outwards, radially. It's pure centrifugal force flinging the fluid away from the center.
So it's adding speed, kinetic energy.
Primarily kinetic energy at that stage, yes. It's converting the mechanical energy from the spinning shaft into fluid velocity. Then here's the next crucial step. As this high-speed fluid leaves the impeller tips, it enters the pump casing, which is called the volute.
The volute, like a spiral shell.
Exactly. It's typically shaped like a spiral, gradually increasing in cross-sectional area. As the fluid enters this widening space, it slows down.
Ah, okay. And slowing down does what?
Well, energy has to be conserved, right? So as the kinetic energy speed decreases, it gets converted into potential energy, which in this case is pressure. The volute's shape is designed specifically to manage this conversion efficiently.
So the impeller gives it speed, the volute converts that speed into pressure.
That's the fundamental process. Spin fast, fling out, slow down, build pressure. It's quite elegant.
It really is.
Yeah.
Okay, so how do we, quantify that energy transfer? If an engineer wants to calculate how much energy the pump is actually adding, is there a specific concept for that?
Yes, absolutely. This is where the concept of head comes in, specifically the net head, often written as HNet.
Net head, okay.
It's basically a measure of the total useful energy added to the fluid by the pump, expressed as an equivalent height of that fluid column. It accounts for all the energy gains.
And there's an equation for that, right? Looked a bit complex.
There is. The full equation is HNet Pout Pin plus Faut Vin 2 Quilladri plus Zout Zin. Looks intimidating, maybe, but each part tells a story.
Okay, break it down for us. Like, what does each term actually mean in terms of energy?
Sure. Think of the total energy in the fluid having three main components. The first term, Pout Pin, that's the pressure head. It represents the increase in static pressure the pump creates, converted into an equivalent height. Pout is outlet pressure, Pin is inlet pressure, Rho is fluid density, G is gravity. It's the push energy added.
Okay, pressure difference converted to height. Got it.
The second term, Vout to Vin to G, is the velocity head. This represents the change in the fluid's kinetic energy, its speed also converted to an equivalent height. The pump makes the fluid move faster from inlet Vin to outlet Vout. That's the speed energy added.
Or the energy of motion.
And the last term, Zoutzin, is the elevation head. This one's simpler. It's just the physical change in height between the pump's outlet and inlet. If the pump is lifting the fluid upwards, this term accounts for that gain in gravitational potential energy, the lift energy.
So HNet is the sum of the gains in push, speed, and lift energy, all expressed as a height the pump could theoretically lift the water.
Exactly. It's the total useful energy increase per unit weight of fluid, a really fundamental measure.
That clarifies it a lot. So, knowing the net head, how do we talk about the pump's power? Like in horsepower or watts?
Good question. We have a couple of key power metrics. First is the water horsepower, sometimes called hydraulic horsepower. We can note it as water horsepower.
Water horsepower.
This is the actual useful power delivered to the fluid. It's directly calculated from the net head and the flow rate. The formula is water horsepower, Rj H net.
Okay, Rg V dot H net. So density, gravity, volume, flow rate, V dot. And the net head we just figured out. Makes sense, more flow or more head means more power delivered to the water.
Precisely. That's the useful output. But, and there's always a but in the real world.
Ah, yes. Efficiency isn't 100%.
Never. Pumps, like all machines, suffer from irreversible losses. Energy gets wasted.
What kind of losses are we talking about? Just friction?
Friction is a big one, yeah. Skin friction from the fluid rubbing against the impeller and casing surfaces. But there's also form drag from the fluid flowing around blunt shapes or sharp corners. There's internal leakage, some fluid slipping back from the high-pressure side to the low-pressure side through small gaps. And then there's just general turbulence, chaotic swirls and eddies that dissipate energy as heat.
Wow. Okay. Lots of ways for energy to leak away.
Definitely. Designers work really hard to minimize all of these, but you can't eliminate them entirely.
So the power you actually have to feed into the pump shaft has to cover both the useful water horsepower and all these losses.
Exactly. And that input power, the mechanical energy supplied to the pump shaft, is called the brake horsepower, or BHP.
Brake horsepower. Okay.
For a pump driven by a motor turning a shaft, we can calculate it if we know the shaft's rotational speed, at omega in radians per second, and the torque being applied to the shaft, T-shaft. The formula is simply BHP acceptance.
Torque times rotational speed. That's the raw mechanical input power.
Correct.
Which leads us naturally to efficiency.
Right on cue. Pump efficiency, usually denoted by the Greek letter eta, E-pump. This is maybe the most important single performance metric for a pump user.
Because it tells you how much bang you're getting for your buck, energy-wise.
Precisely. It's the ratio of the useful power you get out, the water horsepower, to the total power you put in, the brake horsepower. So E-pump equals W water horsepower BHP.
Simple ratio. Output over input.
Yep. A higher efficiency means less wasted energy, lower operating costs, smaller motors needed. It's crucial for economic and environmental reasons. Even a few percentage points difference can mean huge savings over the pump's lifetime.
Absolutely critical. Okay, let's dig even deeper now into the physics. You mentioned the Euler turbo-machine equation. Sounds pretty fundamental.
It really is. It's a cornerstone equation for understanding turbo machinery, both pumps and turbines. It might sound complex, but the core idea is actually derived from a fundamental physics principle, the conservation of angular momentum.
Angular momentum, like rotational momentum.
Exactly. We apply this principle to the fluid as it passes through the rotating impeller, looking at a specific control volume from the inlet radius, let's call it R1, to the outlet radius R2.
Okay.
The equation essentially says that the torque supplied to the pump shaft, Q shaft, is equal to the rate at which the angular momentum of the fluid changes as it goes from R1 to R2.
So the turning force on the shaft directly relates to how much the fluid spin changes.
Precisely. It links the mechanical input, torque, directly to the fluid dynamics, change in angular momentum. The equation itself is T shaft equals a V dot, R2, V2, or I1, V1T.
Okay, let's unpack that. Rho is density, V dot is flow rate. We know those. What are V1T and V2T?
Those are the tricky bits. V1T is the tangential component of the fluid's absolute velocity at the inlet radius R1, and V2T is the tangential component of the absolute velocity at the outlet radius R2.
Tangential component, meaning how fast it's moving around the center, not straight out.
Exactly. Think of a point on a spinning merry-go-round. Its tangential velocity is how fast it's moving sideways around the circle. So V1T is how much spin the fluid has as it enters the impeller, and V2T is how much spin it has as it leaves. The pump's job is to massively increase that tangential velocity, V2T, compared to V1T.
Ah, okay. So the pump adds torque, which increases the fluid's rate of spin, which is related to the energy transfer.
That's the essence of it. The difference, R2VT or 1V1T, represents the change in angular momentum per unit mass, and multiplying by the mass flow rate, V dot, gives the total rate of change, which equals the applied torque.
This sounds like a very clean, idealized picture. How does it match up with designing real pumps?
That's the key question. The Euler equation gives us the theoretical ideal torque and head, but achieving that ideal in practice is, well, extremely difficult.
Why is that? What makes it so hard?
Well, for instance, the equation assumes the fluid perfectly follows the blade angles, that the velocity is uniform across the inlet and outlet, that there's no slip between the blades and the fluid. Lots of idealizations.
Real fluid doesn't behave that nicely.
Not usually, no. You get flow separation, turbulence, recirculation, all sorts of things that cause the actual performance to deviate from the Euler prediction. Designers use the Euler equation as a starting point, a theoretical maximum, but then they have to incorporate corrections and rely heavily on experimental data and computational fluid dynamics, CFD, to predict real-world performance.
So things like blade angles, they're designed based on this theory, but with real-world adjustment.
Absolutely. Designers carefully choose the inlet blade angle, Botello 1, and the outlet blade angle, Botello 2. These angles are critical because they determine how the fluid enters and leaves the impeller relative to the blade itself. They try to set deskly 1 so the fluid enters smoothly, ideally with minimal shock or incidence, especially at the design flow rate.
Design flow rate, meaning it only works perfectly at one specific flow.
Often, yes. The optimal angle might only be perfect for one particular flow rate. If you operate the pump significantly above or below that point, the fluid might hit the blades at an awkward angle, causing losses. So there's a trade-off between peak efficiency at one point and good performance over a wider range.
And they also consider the absolute flow angle, AGI.
Yes, RU1 is the angle of the fluid's absolute velocity path relative to the tangential direction. And the normal velocity components, V1 and V2n, are related to the flow rate Q and the flow area A at the inlet and outlet, Vn equals QA. All these angles and velocities are interconnected through vector triangles, which designers use extensively. It's quite geometric.
It sounds incredibly complex to get right. Microadjustments having big impacts.
It can be, yeah. Especially minimizing those losses we talked about, preventing flow separation off the blades, managing the pressure distribution to avoid cavitation. It's a real balancing act, using geometry, fluid dynamics principles, and often a lot of testing and refinement. It's about guiding the fluid as gently and effectively as possible.
Okay, shifting gears slightly. Let's talk about putting these pumps into actual systems. One big practical challenge is getting the water into the pump in the first place, especially if the water source is below the pump. This idea of suction head.
Yes, suction head, or more formally, the net positive suction head, NPSH. This is absolutely critical for practical pump operation, and it relies heavily on atmospheric pressure.
Atmospheric pressure, how does that help suck water up?
Well, technically, pumps don't suck water. What they do is create a low pressure zone at their inlet, the suction side. The pressure outside, the atmospheric pressure acting on the surface of the water source, like a tank or a river, is then higher than the pressure inside the pump inlet. It's this pressure difference that actually pushes the water up the suction pipe and into the pump.
Ah, okay. So the pump lowers the pressure and the atmosphere does the pushing.
Exactly. At sea level, standard atmospheric pressure is about 14.7 psi.
So there must be a limit to how high the atmosphere can push the water, right? Even if the pump made a perfect vacuum.
Absolutely. 14.7 psi can support a column of water about 33.9 feet high, or roughly 10.3 meters. That's the theoretical maximum suction lift at sea level, assuming you could create a perfect vacuum and ignoring all losses.
33.9 feet. But
Yeah.
you never get that in practice, do you?
Not even close. In the real world, the practical suction lift for most centrifugal pumps is limited to maybe 26 feet, often less, sometimes significantly less, maybe 15 or 20 feet, depending on the setup and the fluid.
Why such a big difference? What brings it down from 34 feet to, say, 26 or less?
Several factors chip away at it. First, you have friction losses in the suction pipe itself. The water rubbing against the pipe walls, going through bends, valves, strainers. All that uses up some of the pressure difference.
Okay, friction steals some of the atmospheric push. What else?
The big one is the need to prevent cavitation. This is the real killer.
Cavitation, you mentioned that briefly. Sounds bad. What is it exactly?
It's essentially the water boiling inside the pump, but not because it's hot. If the pressure inside the pump, especially at the eye of the impeller, where pressure is lowest, drops below the vapor pressure of the water at its current temperature.
Vapor pressure. The pressure at which it wants to turn into steam.
Exactly. If the local pressure drops below that point, tiny bubbles of water vapor will form spontaneously.
Okay, tiny steam bubbles. So what?
Well, these bubbles get swept along with the flow into areas of higher pressure within the pump, usually as they move out along the impeller vanes, and when they hit that higher pressure, they collapse violently.
Yeah.
It's an implosion happening thousands of times per second.
Implosions. That sounds damaging.
Extremely. Each tiny implosion creates a microjet of water and a shock wave that hammers the impeller surface. It sounds like gravel is running through the pump. Over time, it physically erodes the metal, causing pitting and severe damage, drastically reducing performance and eventually leading to failure.
Wow. Okay, so you absolutely have to keep the pressure above the vapor pressure to avoid destroying the pump?
Precisely. That's the net positive suction head required, NPSHR, the minimum pressure margin needed at the pump inlet above the vapor pressure to prevent cavitation. And ensuring the pressure available, NPSHA, is greater than NPSHR dictates your maximum practical suction lift. It's often the limiting factor.
That makes perfect sense, a crucial practical limit. Okay, so beyond getting water in, how do we figure out how a specific pump will actually perform in a specific pumping system? This sounds like where those curves come in.
Exactly. This is where we use pump characteristic curves and system curves. It's fundamental to matching a pump to its job.
Let's start with the pump curve. What does that show?
The pump characteristic curve, sometimes called the HQ curve, shows the relationship between the head the pump can deliver and the flow rate Q it produces. It's specific to that particular pump model operating at a certain speed.
So it's like the pump's performance menu. Here's the head I can give you at different flow rates.
Pretty much. Typically, the curve starts at its highest head value when the flow rate is 0. This point is called the shutoff head, 80.
Shut-off head. Meaning if you closed a valve right at the pump outlet, max pressure, no flow.
Exactly. Then, as you allow more flow, the head the pump can generate generally decreases. The curve slopes downwards.
And our sources gave an equation for this, like available H0 AQ2. Is that typical?
That parabolic form is a common approximation, especially for centrifugal pumps over their typical operating range. H0 is the shutoff head, and a Kummerer is a coefficient related to the pump's internal losses and design, determining how quickly the head drops off with increasing flow Q. At the other end, where the curve hits 0 head, that flow rate is called the free delivery discharge, the maximum flow the pump can push with no back pressure.
So the curve maps out the pump's capability envelope from max head 0 flow to 0 head max flow.
Precisely. That's what the pump can do.
Okay, so what's the system curve then?
The system curve, required, represents the other side of the equation. It shows the head that the piping system itself requires to make a certain flow rate Q through it. It's completely independent of the pump.
So this is about the pipes, the elbows, the valves, the height difference. Everything except the pump.
Exactly. It represents the resistance of the system. It's the head needed to overcome two main things: the static elevation difference and the dynamic losses.
And the equation for this often looks like H required equals Z2 Z1 plus BQ2.
That's a very common form. The Z2, Z1 term is the static head, simply the vertical height difference between the outlet point and the inlet point. You have to lift the fluid that high regardless of flow rate.
Makes sense. Gravity doesn't care about flow.
Right. And the BQ2 term represents all the dynamic losses, friction in the pipes, losses through fittings like elbows and valves, entrance and exit losses. These losses are highly dependent on flow rate, generally increasing with the square of Q.
So the faster you try to push fluid through the system, the exponentially higher the resistance gets.
Basically, yes. The B coefficient captures all those system-specific resistance factors.
Okay, so we have the pump curve, what the pump can do, and the system curve, what the system needs. How do they come together?
The magic happens where they intersect. The operating point of the pump in that specific system is the point where the pump characteristic curve crosses the system curve.
The intersection.
Yeah. At that single point, the pump is capable of delivering available exactly matches the head the system requires, H required for that particular flow rate. That intersection defines the actual steady state flow rate, Q and head H, at which the system will operate.
So supply meets demand, right there on the graph.
Couldn't have said it better. That's where the system balances out.
Do we have a quick example, like plugging in some numbers?
We do. Let's use the example from the source material. Suppose we have a pump with a curve H is 0.0453 Q2. Here, shutoff head H0 is 5.3 meters, and the coefficient A is 0.0453 Q2.
Okay, pump curve defined.
And it's installed in a system with a curve H equals 3.52 plus 0.0261 Q2. So the static lift, Z2, Z1, is 3.52 meters, and the loss coefficient B is 0.0261 mil N2.
Got it. Pump supply system requires. How do we find the operating point?
We just set available equal to H required, so
Right.
5.3, 0.0453 Q2 equals 3.52 plus 0.0261 Q2.
Okay, we need to solve that equation for Q. Looks like we gather the Q squared terms on one side, the constants on the other.
Exactly. If you rearrange it, you get 0.0453 plus 0.0261 Q2 equals 5.3, 3.52.
Yeah.
That simplifies to 0.0714 Q2 equals 1.78.
So Q2 equals 1.78, 0.0714, which is about 24.9, taking the square root.
Gives you Q approximately equal to 5.0 liters per minute.
Okay, so the operating flow rate is 5 elements. How about the head at that point?
We can plug Q5 back into either equation. Let's use the system curve. H equals 3.52 plus 0.026152. That's 3.52 plus 0.0261 plus 0.52 plus 0.65.
Giving us H equals 4.17 meters.
Right. So the operating point is 5 milliamps at 4.17 meters of head. That's where this pump will run in this system.
And that 0.65 meters we calculated, that was the head loss, the BQ2 part.
Exactly. Out of the total 4.17 meters of head the pump provides, 3.52 meters is just lifting the water, static head, and the remaining 0.65 meters is used up overcoming friction and other dynamic losses in the system.
So about, 15-18% of the energy is just fighting system resistance in this case?
Yep, around 18%. It really highlights how important system design is. Minimizing those losses by using smoother pipes, fewer bends, right-sized components, it directly impacts how much useful work the pump can do.
Absolutely. Okay, now what if one pump isn't enough? What if you need more head or more flow than a single unit can provide? This brings us to combining pumps. Let's talk about pumps in series first. What's the goal there?
Putting pumps in series, connecting the outlet of one directly to the inlet of the next, is primarily done to increase the total head delivered at a given flow rate.
So stacking them up makes them push harder, essentially.
That's a good way to think of it. The head generated by each pump adds together. If you have two identical pumps in series, they'll deliver roughly double the head at the same flow rate compared to just one pump running alone.
Okay, and a typical use case might be needing to pump water really high, like that 30-meter example in the sources.
Exactly. If the required static lift plus the expected friction losses exceed what a single practical pump can deliver efficiently, connecting multiple pumps in series is a common solution.
When engineers choose pumps for a series setup, what are they thinking about? Just adding up the heads.
Adding heads is the basic principle, but there's more to it. As the sources mention, they often try to use fewer, smaller, more economical pumps if possible. A big consideration is estimating the head loss in the system. You need the combined head to be comfortably above the static lift, plus those losses at your target flow rate.
Right, you need some margin for friction.
Absolutely. The sources gave that example with 4 different pumps, aiming for 30 meters of lift at 2 liters per minute.
Yeah, pump 1 gave 8-meter head, pump 2 gave 12 meters, pump 3 gave 11.5 meters, and pump 4 gave 14 meters, all at 2 element.
So to get over 30 meters, you need combinations. Like pumps 1, 2, and 3, that's 8 plus 12 plus 11.5 equals 31.5 meters.
Just a little over 30 meters, That might be good if losses aren't too high.
Could be the most economical choice, yeah. But what if losses are higher? Maybe you need pumps 1, 2, and 4. That's 8 plus 12 plus 14 plus 14 is even more headroom for losses.
Or even pumps 2, 3, and 4. 12 plus 11.5 plus 14 equals 37.5 meters. That's quite a bit over 30 meters.
Right, and maybe that's too much. If you provide way more head than needed, you might force too much flow through the system, or you'd have to throttle it with a valve, which wastes energy. It's an optimization problem matching the combined pump performance to the system's needs, including a sensible allowance for losses without being excessively oversized.
It really shows the interplay. Let's see how putting pumps in series affects that operating point we calculated earlier. If we took two of those identical pumps from the example, H equals 5.30.0453 Q2, and put them in series in that same system, H equals 3.52 plus 0.0261 Q2.
Okay, so with two identical pumps in series, their combined head characteristic curve is roughly double the head of a single pump at any given flow rate. So the new available becomes 5.30.0453 Q2.
Correct, and the system curve stays the same. H required equal 3.52 plus 0.0261 Q2. Now we set these equal to find the new operating point.
Okay, 10.6, 0.0906 Q2 plus 3.52 plus 0.0261 Q2. Rearranging, we get 0.0906 plus 0.0261 Q2 equals 10.6, 3.52.
That's 0.1167 Q2 equals 7.08.
So Q2 equals 7.08, 0.1167, which is about 60.67.
Yeah.
Square root of that gives a new flow rate Q of about 7.8 liters per minute.
7.8 liters. That's a big jump from 5 levels with a single pump. What about the head?
Plug Q 7.8 back into the system curve. H equals 3.52 plus 0.0261, 7.82. That's 3.52 plus 0.0261, 60.84, approximately 3.52 plus 1.59.
Which gives H equals 5.11 meters.
Right. So the new operating point is 7.8 lilins at 5.11 meters.
Interesting analysis there. We doubled the theoretical pump head capability, but the actual operating head only went up from 4.17 meters to 5.11 meters, about a 20% increase.
Yeah.
But the flow rate jumped from 5 to 7.8 meters, over a 50% increase.
Exactly. It really demonstrates how the system curve dictates the outcome. Because the system resistance, BQ2, increases sharply with flow, a lot of the extra head provided by the second pump gets eaten up, just overcoming the higher friction at the higher flow rate. You get significantly more flow, but diminishing returns on the head increase.
Fascinating how the system pushes back.
Yeah.
Now, series is for head. What about connecting pumps in parallel? You mentioned that briefly.
Right. Parallel connections, where pumps take suction from a common source and discharge into a common header, are used primarily to increase the flow rate at a given head.
So side-by-side pours for more volume.
Essentially, yes. At any given head value, the flow rates from the parallel pumps add together. If you have two identical pumps in parallel, they'll deliver roughly double the flow rate at the same head compared to a single pump.
Like needing to fill a big tank faster or supplying water to a city where demand varies?
Perfect examples. Large water supply systems, industrial cooling loops, situations where you need high capacity or variable capacity by staging pumps on and off. You add pumps in parallel to meet higher flow demands.
Are there any tricky parts to running pumps in parallel?
One key challenge is ensuring they share the load reasonably well, especially if the pumps aren't identical or if the piping isn't symmetrical. You also need to make sure each pump is operating on a stable part of its curve and that one pump doesn't force the other into an inefficient or damaging operating condition. It requires careful system design and sometimes check valves to prevent backflow through a pump that's not running.
Different set of challenges than series, okay? That covers combining pumps. Now let's pull back a bit and connect some dots. We've focused heavily on pumps, but you mentioned the Euler turbo machine equation applies to turbines too. Is there a deeper connection there?
Absolutely. That Euler equation is truly universal for ideal turbo machines. It underscores that pumps and turbines are fundamentally related, just operating in opposite directions of energy transfer.
How does the equation change for a turbine?
The principle is the same torque is related to the change in angular momentum. But for a turbine, the fluid is giving up energy, so the flow path is reversed. High-energy fluid enters at the larger radius, what was R2 for the pump, and exits at the lower radius, R1. The turbine extracts torque from the fluid, causing a decrease in the fluid's angular momentum. R1v1t will be less than R2v2bt, or the term might even become negative depending on design.
So the same physics just run backwards, energy-wise.
Exactly. It's a beautiful symmetry.
And this connection extends to the design tools too, like velocity triangles. They're used for turbine runners, just like pump impellers.
Oh, absolutely. Velocity triangles are essential for designing both. They allow engineers to visualize and calculate the fluid velocities, absolute relative to the blade, tangential, normal components, and the flow angles and blade angles at both the inlet and outlet.
And the goal is always to optimize that fluid-blade interaction.
Always. For a pump, you're designing the blades to add energy efficiently, minimizing losses. For a turbine, you're designing them to extract energy efficiently, again minimizing losses. The blade angles, number 2, are critical fixed parameters chosen to achieve the desired performance, guiding the fluid smoothly onto and off the rotating element.
It really emphasizes how critical that blade geometry is.
Yeah.
Sculpted for performance.
Definitely. Designers manipulate inlet-outlet radii, blade widths, and those crucial angles to control the velocity components and maximize energy transfer, either adding power efficiently or extracting power effectively. Turbines.
This brings us to a really interesting concept you touched on earlier, swirl. The rotation of the fluid leaving the machine. Why is this so important?
Swirl, specifically the amount and direction of tangential velocity re-raining in the fluid as it exits the rotor, has significant implications for efficiency and losses. It's characterized by that outlet absolute flow angle, AI1, using turbine notation where 1 is the outlet.
Okay, and you mentioned 3 types.
Broadly, yes. First, no swirl, where I1 equals 0 degrees. The fluid exits purely axially or radially, depending on the machine type, with no rotational component relative to the casing. This is often an ideal goal, meaning you've extracted or added as much angular momentum as possible.
Leaving no spin behind. What are the others?
Rotational swirl, where IL1 0, the fluid leaving the rotor is still spinning in the same direction as the rotor itself. This often means you haven't extracted all the possible energy in a turbine, or you've left some rotational energy behind in a pump. However, it can sometimes lead to lower friction losses in the downstream ducting because the flow is less chaotic.
Okay, spinning with the rotor, and the last one was?
Reverse swirl, where IO1 0. This is where the fluid exits spinning in the opposite direction to the rotor's rotation.
Opposite direction. How does that happen? And what's the effect?
It happens in some high-performance turbine designs. Theoretically, having V1T be negative, opposite to the blade speed, can maximize the change in angular momentum, R2V2, RO1V1T, potentially leading to the highest theoretical power output according to the Euler equation.
Maximizing the difference by making the second term negative. Clever, but sounds problematic.
Extremely problematic in practice. While it looks good on paper for power output, reverse swirl creates incredibly high shear and turbulence between the exiting fluid and the downstream components, and often within the rotor passages themselves. The friction losses become enormous, often wiping out any theoretical power gain. Plus, it can induce very high stresses and instability.
So a theoretical maximum that's practically a disaster zone.
Often, yes. It's a perfect example of the complex trade-offs designers face. They have to balance theoretical performance gains against real-world losses, stresses, and stability. Understanding and controlling swirl, minimizing unwanted swirl in pumps, or carefully managing it in turbines is crucial for optimizing efficiency and ensuring reliable operation. These are universal principles across turbo machinery.
Wow, what an incredibly detailed journey into the world of pumps. We really covered a lot today. We started with the basics, defining hydraulic machinery, looked at positive displacement versus turbo machines, and then really zoomed in on pumps, axial, radial, especially centrifugal pumps. We unpacked how impellers work, the meaning of net head using Bernoulli's principles, and the power of the Euler turbo machine equation. Then we got practical, tackling suction head limits, the dangers of cavitation, and the absolute necessity of matching pump curves with system curves to find that crucial operating point.
That intersection is key.
Absolutely. And we even explored how combining pumps in series boosts head, looking at a real selection process and how the system itself impacts the outcome. All fundamental stuff for anyone starting in hydraulics.
It really lays the groundwork. And thinking about that operating point, how it depends on both the pump and the system, it makes you wonder, doesn't it?
Wonder what?
Well, here's a thought for you, our listeners, to chew on. We always talk about selecting the right pump for the system, but what if we flipped it? Knowing how much the system dictates performance, how could we use innovative system design, maybe smarter pipe routing, low-loss fittings, active flow control, even new materials to unlock major efficiency gains or new capabilities, perhaps even allowing us to use simpler or smaller pumps. Could the next big leap come from the system, not just the pump?
That's a fantastic point. Shifting the focus from just the component to the entire interacting system. A great thought to end on. Well, this was just our first deep dive into hydraulics. We've only scratched the surface. There's so much more turbines in detail, valves, actuators, control systems. We'll be exploring more in future deep dives. So please stay tuned. Thanks for joining us today on the Deep Dive.